Welcome back to our second slot. We still are talking electrical power, but now we want to look at the different quantities in terms of voltage, current, and resistance, how exactly they impact the power of an electrical device in a circuit. Okay, now we understand that for us to measure power in a circuit, we need to have voltage and current basically. So the voltmeter connected across a component will give us an indication of how much work is done per coulomb of charge across that component, while the ammeter reading gives us the current to say how many coulombs of charge pass through a point per second. So knowing that P is equals to VI, that's the basic, okay? Now we also know that from the Ohm's law, we've got V is equals to IR, okay? So in the event that we don't have, you know, the voltage in a particular circuit, we are able to determine power using P is equals to, so this is our V, okay? Just to quickly show you how we arrived at one of the three formulae. It's that P is equals to, where there is V, we've got IR, so that's our V multiplied by I, okay? So this gives us P is equals to I squared multiplied by R. So we would use this equation to calculate the power of an electrical device if we know how much current passes through that device given its resistance. However, if we have a situation where we do not have the current, and then from the Ohm's law, we know that I is equals to V over R, okay? And then we know that P is equals to VI, okay? Now, if we know that P is equals to VI, then we'll have P is equals to a V, where this I will have I over, we'll have V over R instead, okay? So we'll have V over R, just to correct that, okay? So if we have the voltage, so that's our current, which is V over R, then this gives us P is equals to V squared over R. So these are the three formulae that would use to determine power in an electrical circuit. Now, let's focus our attention on a simulation to look at, you know, a simple example whereby we have a light bulb, and then we're going to vary the voltage from the source, which is the battery, and see how it affects the power, you know, in an electrical circuit, all right? Okay. Now, let's go to the simulation, all right? So here we have a simple circuit. We've got a cell, which is a source. This cell, we will start the voltage with a voltage of 3 volts. It's an open switch, which explains why there's zero current, okay? And then the resistance of the light bulb shall keep the same at 10 ohms. We just want to see how the power is affected by changing the voltage. We already know that from the Ohm's law, the voltage and current are directly proportional, provided that temperature remains constant. So if we complete the switch, the circuit by closing the switch, there is a reading. So the voltage of the battery is 3 volts, okay, across the 10 ohm resistor. So if we were also to measure the voltage across the light bulb, it will actually give us 3 volts, which is actually the voltage across the source, okay? So all the terminal potential difference is equals to, you know, the EMF of the source, okay? So the 3 volts goes with the current of what? 3 amperes, 0.3 amperes, okay? What if we double the voltage of the source and see how that affects the current voltage, and then would also see the magnitude of, and maybe just get a trend on the magnitude of the power of that is dissipated by the light bulb. So instead of 3, now we double that, it goes to 6 volts, okay? So if it goes to 6 volts, you can immediately see that the current has also increased from 0.3 to 0.6, and that in turn has affected the brightness of the bulb. The bulb is now actually glowing much brighter. So if we measure the voltage across the bulb, it gives us 6 volts, which corresponds to a current of 0.6 amperes. This voltage is the same as that across the source, which is 6 volts, okay? What happens then, I think we'll get the pattern. What happens if we make even voltage bigger, 3 times as bigger as the original one? So this takes us to 9 volts. You can see the brightness is getting higher and higher. And again, the voltage across the light bulb is 9 volts. Current is also increased, okay? Now, let's do the last one, making it 4 times as bigger. So if the voltage that the source supplies is 9, what about if it's 12, okay? Right? The brightness is even increased. The current is increased to 1.2 amperes. So has the voltage across the what? The source, okay, which is 12 volts. Right. Now, let's go back to our slide and talk the science behind that, okay? Okay. Now, these are the values that we actually managed to verify, okay? The voltage across the light bulb was increasing in multiples of 3, okay? Look at the pattern in terms of the power, okay? Remember, if voltage increases, so does current. This is based on Ohm's law, which says V is directly proportional to current, provided temperature is constant, right? If temperature remains constant, current and potential difference are actually directly proportional, okay? So it's on that background, okay? Right, now if you look at the resistance of the light bulb, we did not change it. It remained the same. No, the potential difference across the light bulb, when it increases, so does the current, okay? And then the product of, you know, our current and voltage, which is P is equals to VI, that gives us the power, okay? So actually this 0.9, we got it from saying, what's the voltage reading? It was 3 volts, and then the current reading, 0.3 amperes, okay? So this gives us a product of 0.9 watts, okay? That's the power, okay? So this is how we managed to obtain these values. Now, if we look at the trend and pattern, what is very true is that as we increase the voltage, also the current will increase. But that how did that affect the brightness of the light bulb? As the current increased, as more and more current moved through the light bulb, there was greater brightness or increased brightness, right? Okay, now from the results we obtained, okay, when resistance remained constant, this is a condition that's very important for us to actually qualify that relationship. Okay, sketch the following graphs: the graph of power versus voltage and the graph of power versus current. But if we are to start with the power versus voltage, you'd realize, if we quickly go back to, you know, the table of results that we obtained from the simulation, we can see that this is not necessarily a linear relationship. But remember, P is equals to I squared R. At the same time, we're saying P is equals to V squared over R. So if R in both cases is constant, this doesn't give us a linear relationship, okay? So from the graph, we can immediately say, okay, in terms of, so we'll have P on the vertical axis, P in watts, as well as volts, the voltage in volts, okay? That's what it is. And then we get this kind of a relationship, okay? Because we are saying this is based on P is equals to V squared, okay, over R. While the same would happen with the current. Power in watts, okay? And then we've got current in amperes, okay? Again, this is based on the equation P is equals to I squared R, okay? Remember, the resistance was kept constant in both equations. Now, we also get that kind of a relationship between those two. Very, very important, okay? Now, we want to predict a relationship that exists between power and voltage. Let's agree that these are not linear relationships, okay? Okay, what do we mean by that when we're saying they are not linear relationships? Remember, if two quantities are directly proportional to each other, it means if you increase one, the other one will also increase by the same proportion. So you realize that the moment we say current squared, voltage squared, the proportion doesn't remain the same. It becomes, you know, a curve of some sort, which, as we have shown earlier on. Okay, right. Now, that's basically how we actually put an understanding behind the 3 formulae that we use to determine the power of a a device. Okay. Now we want to predict what happens to the power dissipated by light bulbs connected in series. Okay. First of all, let's agree that when a circuit is in series, it means all the current passes through that point. Current is constant. Okay. This is what we already know. Current is constant. And then we also know that in a series circuit, voltage is divided. Okay? These are very important facts regarding a series circuit. So in this circuit that we'll use, we'll have a battery of 12 volts, and the assumption is that the battery has negligible resistance. So if the battery has got negligible resistance, what does that mean? It means that the internal resistance of the battery can be ignored. In other words, the EMF, which is the maximum amount of energy that the source can supply per coulomb of charge, is actually equal to the terminal potential difference, right? So in this circuit, we'll have two light bulbs which will serve as resistors, okay? So the other resistor has double the resistance of the other, okay? So basically, this is what our circuit would look like, okay? So we just want to compare, what happens in terms of power in that circuit. So let's go to the simulation. Okay, now let's focus our attention on the simulation just to understand what happens in terms of power in a series circuit, right? So if we close the switch, current will start to flow because the circuit is now complete, okay? That's what happens, okay? Now, one of the things that we mentioned, we said the source has a voltage of 12 volts, okay? So that's the energy that it provides per coulomb of charge, while resistor 1, okay, the one that we've highlighted is 10 ohms. Resistor 2 is double that, which is 20 ohms, okay? But we can immediately tell that there is a current in the circuit. The total current in the circuit is 0.4 amperes, all right? So we ask ourselves important questions. How much current passes through resistor 1, which is the 10 ohm light bulb? It will be 0.4 amperes, while the same amount of current actually passes through resistor 2, which is even double the resistance, which is 20 ohms, okay? Now, in terms of brightness, you can tell that these two are quite different, okay? Resistor 2 has got, if we try and look at, the voltage across each one of them. Now, our voltage, in this case, let's measure the voltage across the source, okay? The voltage across the source, we can tell it says it's 12 volts. Now, the 12 volts is split between R1, okay? R1 in this case is 4 volts, okay? So if we say 4 plus the 8, okay, it gives us the 12 volts. This is what we meant when we said that actually voltage is divided, but the current that flows through each of the two resistors is the same. Okay, so in terms of power, which one would dissipate more power? So if we were to determine the power of, that is dissipated by R1, just to compare that so that we can actually understand what is happening there, we would say, okay, so this is our R1, okay? This is our R1, okay? So this is our R1, okay? And then this is our R2, okay? So R1 is actually 10 ohms, okay? While R2 is double that, which is 20 ohms, okay? So P1, which is the power for R1, is equals to the voltage, okay, for 1, which is 4 volts, as it has been measured there, multiplied by the total current, because all the current passes through the 10 ohm, okay? So P1 is actually equals to, what's our V1? It's 4 volts multiplied by 0.4 amperes. So this P1 actually gives us, if we quickly go to our calculator, would get something like 4 multiplied by 0.4, okay? Which gives us what? That value, which is 1.6. So this is 1.6 watts, okay? 1.6 watts. What about for P2? P2 is equals to V2, okay? multiplied by the total current. Why? Because all the current passes through R2. So P2 is equals to, what is our V2? It's going to be 8. The 8 comes from 12 less the 4, okay? Because the total voltage is 12 volts, which can be supplied by the battery, okay? Multiplied by the total current, which is 0.4, right? So P2, that's the power for R2, is equals to, okay, if we go to our calculator, we get something like 8 multiplied by 0.4. Okay, this gives us, we get 16 over 5 as a decimal fraction, which is 3.2. Actually, 3.2 is double 1.6 watts, okay? So the power dissipated by a bigger resistor is actually greater if the same current passes through them, okay? Because what's going to distinguish the quantities that are going to be different as far as R1 and R2 is that R1 is half the resistance of R2, while R2 is double the resistance of R1. This is a very important discovery that if you can look at it, guys, it would say to us that we are saying P, okay, P for, okay, P2 is actually equals to 2P1. The condition is that we said P2, okay, R2 is equals to double R1. So if this is a series, current is constant, okay? The only thing then that changed the value of the power is that the resistance is in that proportion. So as a result, we realize that that's why R2 actually glows brighter than R1. What does that mean? It means it converts a lot of electrical energy into light energy per second compared to R1. So that was the main idea, that if the two light bulbs are connected in series, okay, the one that has got a greater resistance, because the same current passes through each one of them, what's going to happen is that the one that has got greater resistance will transform a lot of energy into other forms per unit time, which is the long and short of it. After the short break, we'll use the very same arrangement of resistors, R1 and R2, one becoming double to each other, and see how that affects the power. Let's take a short break for now.